We just talked about the low-level API for working with I/O, and now we're going to talk about the high-level API, which is also known as STDIO in C, that operates on streams of data or unformatted sequences of bytes. And note that these streams can be of any type, and that file represents an open stream and corresponds to a file descriptor. And file is actually an opaque type, meaning that you can't access its internal representation, that's hidden, which allows for changes down the line that will not affect user code. Instead, users interact with file start pointers through functions like fopen, fread, fwrite, etc., which you've probably seen in some capacity. Now, we also say that these functions are going to buffer data in user memory. And this is an added layer on top of the kernel buffering that we talked about previously. The way this works is when we're using the high-level API, data is first buffered into user memory before being sent to or received from the kernel. So if we're writing, data is first going to accumulate in a user space buffer and then be written to the kernel via the low-level equivalent of write, when the buffer is full or when it's explicitly flushed. And yeah. So most of these functions have pretty similar signatures to the low-level equivalents that we saw before. Note that here, whenever we pass in a file descriptor previously, we're passing in the file start pointer instead. And a few notes on these, I think fread or fopen and fclose are pretty standard and similar to what we talked about before. Fread and fwrite have one difference, which is that with the read and write low-level versions of these calls, we're not guaranteed to read or write the requested number of bytes. In the high-level API, we say that we are guaranteed to read or write the requested number because of the additional buffering that we have and the internal calls to the low-level reads and writes that will eventually wait until the requested number of bytes have been read or read. And we'll see what this actually means in one slide. Yeah. Now, flush is new, and this forces all of the buffer data in memory, in user memory, to be immediately written to the file. So we talked about that first the data with this high-level API is buffered in user memory, and then it's sent to the kernel. This function allows us to force all that data to actually be written from the user buffer. Now, fprintf is similar to printf, except it's going to print to the specified stream based on the format you pass in. And fscanf is the reading equivalent. It allows you to read formatted data from whatever file stream you pass in. So we talked about this briefly, but the difference between fopen and open, besides one being the high-level API and the other being the low-level API, is that fopen is going to return a file pointer while open returns the integer corresponding to the file descriptor. So the file pointer has information under the hood of the file descriptor, but to the user, they don't know what the file descriptor is. They will just use that file pointer to execute further high-level API calls down the road. Okay, and now a more interesting program that actually looks at the different low-level calls. I'm also just going to go straight into this, so if you want to pause the video, feel free. So we first initialize a buffer of 200 bytes. We set all 200 to correspond to the character A, and then we open a file called test.txt. When we write 200 bytes to the buffer, we're going to assume that all of these writes and reads are successful. We write the first 200 bytes, so from the buffer to that file. So now we are at offset 200. Anytime we write or read to a file, we increase the offset as specified. So now we're at offset 200, we've written 200 A's, and now we execute lseek with seek set. If you don't remember what that means that we're doing absolute positioning. So we're starting from the beginning and adding the offset specified here, which is just 0. So we're going to reset the position of that file descriptor or description to be 0. Then we're going to read in from the file to the buffer. We're going to read in the first 100 bytes, which is again just A, and that doesn't do anything because our buffer was already 200 A's. And keep in mind now we're at offset 100 in that file. We again do lseek, but this time with seek cur, which means we use relative positioning, or we start from the current offset and add the specified offset, which is 500. So 100 plus 500, we're now at offset 600 in the file. And in this case, we haven't actually written any characters between those two offsets, so they're just going to be null. Then finally, we write from the buffer, we write 100 characters. Again, this is just a bunch of A's. So we're going to get another 100 A's in that file. And so this is going to clarify kind of what the file looks like. We have the first 200 bytes are A's. Then, because of the way lseek worked, from 200 to 600, they're all null bytes. And then from 600 to 100 characters later, we have A's. Okay, now consider a method that copies n bytes from a source to destination file. You may assume both files are already created and that source is at most 100 bytes long. This method has been written in two different ways, one using the high-level API and another using the low-level API. What is the purpose of the while loops in copy low? So as we talked about before, with read and write, we are not guaranteed to read or write the specified size. This is the low-level API. And with fread and fwrite, we are. So when we're using the low-level API, we're going to use a while loop to keep executing read or write until the requested number of bytes to be read or written is completed. Okay, and last one before we move on to sockets, I think. What does the following program print to standard output? So let's see what's happening. First, we're opening a file called out.txt that now corresponds to new fd. That's the file descriptor. And then we print out the last digit of pi is. When we flush to standard out, that means that any data that was in a user level buffer that was going to eventually go to standard out is going to be forced into standard out. And the reason we do that is because when we now have the dupe2 call, we're redirecting standard out, which is our file descriptor 1, to the file that we opened. So any prints after that are actually, instead of going to standard out, as the default of printf is, they're going to be written to the file that we created that we redirected standard out to. So we're only going to get the last digit of pi is, and then 5 is going to end up as part of our out.txt.